Hello there, and welcome to Galactan Sleep. I'm so glad you found your way here tonight. Maybe your day was long, or maybe it was simply full, the way days become when life asks for your attention again and again. Maybe you're the kind of person who falls asleep best when the mind is given something large and distant to hold on to, something that puts the small worries of Earth into a softer, wider perspective. Or maybe you just like the sound of a calm voice in the dark. Either way, you've come to the right place. Tonight, we're going on a journey. Not outward to the familiar stars you already know, but deeper into the strangest corners of our galaxy. We're going to visit neutron stars. Neutron stars are the collapsed hearts of dead giant stars. They are among the most extreme objects in the entire universe, and yet, they are also among the quietest. They spin in perfect silence. They drift through the black between worlds without hurry, without intention, without any of the noise that fills our human days. Tonight, you have nothing to do but rest, nothing to solve, nothing to remember for tomorrow. Your only task is to lie still, to breathe slowly, and to let your imagination travel to places no human has ever seen, places that exist only in the mathematics of astrophysics and the quiet wonder of a sleeping mind. Just before we begin, if these gentle explorations help you unwind or give you a peaceful way to end your day, consider liking and subscribing to Galactan Sleep. It helps other sleepy souls find their way here too, one drifting mind at a time. And now, let's begin our journey into the most relaxing facts about neutron stars. A neutron star is born from the death of a star much larger than our sun. Our own sun is a gentle, middle-aged star. It will live for about 10 billion years. And when it finally dies, it will swell into a red giant, and then slowly fade into a white dwarf, a quiet, Earth-sized ember cooling over trillions of years. But stars much heavier than the sun live faster and die harder. A star 8 or 10 or 20 times the mass of our sun burns through its fuel in only a few million years, a cosmic blink. And when that fuel runs out, the star's core collapses. Not slowly, not gently, but all at once. The weight of the star's own outer layers comes crashing inward at a significant fraction of the speed of light. That collapse triggers a supernova, one of the most violent events in the universe. For a few weeks, that single dying star can outshine an entire galaxy containing hundreds of billions of other stars. It is a brilliant, final flare of light, a last goodbye before the star transforms into something entirely new. But here is what matters for our peaceful journey tonight. The violence does not last. The supernova fades, the light dims, the shock waves travel outward and eventually dissipate into the thin space between stars. And what remains at the center of all that destruction is a neutron. The violence is over. The star is dead. But its core lives on, compressed into something so small and so dense that it barely seems possible. A neutron star is only about 20 kilometers across. 20 kilometers, that is roughly the distance from one side of a small city to the other. And yet, inside that tiny sphere is packed more mass than the entire sun contains. Our sun is more than 1 million kilometers across. You could fit more than 1 million Earths inside the sun, and a neutron star, smaller than most cities on Earth, holds more mass than that enormous, glorious sun. Think about that for a moment as you lie there in the dark, a ball of matter no wider than a morning commute, but so heavy that its gravity bends light, warps time, and holds together against forces that would tear any ordinary object apart. And it sits there in silence, spinning slowly or quickly, but always quietly, asking nothing of the universe. Because the neutron star is so small and so heavy, its surface gravity is unimaginably strong. If you stood on the surface of a neutron star, which you could never do because you would be torn apart instantly, you would feel gravity about 200 billion times stronger than what you feel on Earth. 200 billion times. A single grain of sand dropped from a height of 1 centimeter would hit the surface with the force of 1,000 tons of TNT. A marshmallow would strike with the energy of a hydrogen bomb. But of course, no human will ever stand on a neutron star. No machine we could build would survive even a microsecond on that surface. The neutron star keeps its distance from us, and we keep our distance from it. That is part of its peaceful nature. It exists in a realm we can only imagine, safely far away, spinning quietly in the dark. A single teaspoon of neutron star material weighs as much as a mountain. Let me say that again in a slightly different way so your mind can rest. A teaspoon, the kind you might use to stir honey into tea or to measure sugar for baking, If that teaspoon were filled with matter from the inside of a neutron star, it would weigh approximately 1 billion tons. That is roughly the weight of Mount Everest compacted into the volume of your cupped hand. The reason for this extraordinary density is that ordinary matter is mostly empty space. In the atoms that make up your body, your bed, the air in this room, the distance between the nucleus at the center of each atom and the electrons orbiting around it is enormous compared to the size of the nucleus itself. If you removed all the empty space from every atom in a human body, the entire human race would fit inside a sugar cube. But in a neutron star, gravity has already removed that empty space. When the original star collapsed, the pressure became so intense that electrons and protons were forced together to form neutrons. And those neutrons were then packed against each other, with no space left between. The result is a material so dense that it cannot be created in any laboratory on Earth. It can only exist in the hearts of dead stars. And there it rests, quiet and heavy and perfectly still, a single teaspoon of it heavier than anything you have ever touched, or seen or imagined. Neutron stars spin incredibly fast, much faster than our sun. Our sun rotates once every 25 days or so at its equator. That is a leisurely pace, calm and unhurried. But when a star collapses into a neutron star, something called conservation of angular momentum takes over. You've seen this before, even if you didn't know the name for it. When a spinning ice skater pulls their arms in toward their body, they spin much faster. The same total spin, the same angular momentum, but distributed over a smaller radius. When a star's core collapses from something hundreds of thousands of kilometers across down to something only 20 kilometers across, its rotation speed increases dramatically. A star that took 10 days to complete one rotation before its death might, as a neutron star, spin hundreds of times every single second. Some neutron stars, the fastest ones, rotate more than 700 times per second. That means their surfaces are moving at a significant fraction of the speed of light, and yet, from a distance, you would never know they were spinning at all. They look like perfectly still points of faint light, or often, no light at all. Their motion is invisible, silent, and impossibly fast, like a fan blade spinning so quickly that it appears transparent. The neutron star turns and turns and turns in the dark, carrying the memory of its former star in every rotation, but making no sound at all. Some neutron stars are called pulsars because they send out regular beams of radiation. Not all neutron stars are pulsars, but many are. A pulsar is a neutron star that has beams of energy shooting out from its. These beams are made of radio waves, sometimes visible light, sometimes X-rays or gamma rays. Because the neutron star spins, and because the magnetic poles are usually not aligned with the rotational axis, these beams sweep through space like the beam of a lighthouse. If you have ever stood near a lighthouse at night, you have seen how the light seems to flash on and off as it rotates. That is exactly what a pulsar does, but with radiation instead of visible light. If one of those beams happens to point toward Earth, we detect a regular pulse of energy each time the star rotates. The timing is so exact, so precise, that some pulsars rival atomic clocks for accuracy. The most stable pulsars vary by less than a millionth of a second over years of observation. You could set your watch to a pulsar if you had a way to travel millions of light years to read it, but you do not need to. The pulsar does not need you to. It simply spins and pulses and spins and pulses, a cosmic metronome keeping time for no one but itself, in the silent darkness between the stars. And as you lie here, somewhere in the galaxy, perhaps a dozen pulsars are sweeping their beams through space, and not one of them is aimed at you. They are just turning peacefully, eternally, alone. The magnetic fields of neutron stars are the strongest known in the entire universe. Earth's magnetic field is what makes compass needles point north, and what creates the beautiful auroras near the poles. It is strong enough to protect our atmosphere from the solar wind, and we barely notice it in our daily lives. The magnetic field of a neutron star is trillions of times stronger than Earth's. 1,000 trillion times stronger. If a neutron star were as close to us as the moon, its magnetic field would disrupt the very structure of atoms in your body. It would pull the iron from your blood, scramble the electrical signals in your neurons, and tear molecules apart at the quantum level. But neutron stars are never that. They are scattered across the galaxy at vast distances, hundreds or thousands of light years away, wrapped in invisible magnetic cocoons that warp the space around them. These magnetic fields store enormous amounts of energy. Sometimes, that energy is released in bursts that we can detect from Earth as gamma-ray flares or X-ray pulses. But most of the time, most neutron stars, the magnetic field simply exists. It does nothing dramatic. It does not announce itself. It is just there, a silent shroud around an object so strange that our human minds can barely hold on to it, and there is something peaceful about that, something calming about the fact that the most extreme magnetic fields in the cosmos are also some of the quietest, demanding nothing, destroying nothing, simply being. Some neutron stars are called magnetars, and they have magnetic fields 1,000 times stronger than ordinary neutron stars. Magnetars are the extreme of the. If an ordinary neutron star has a magnetic field trillions of times stronger than Earth's, a magnetar's field is quadrillions of times stronger. To give you a sense of scale, a magnetar's magnetic field is so intense that it would strip the information from every credit card within hundreds of thousands of kilometers. It would pull the iron atoms from your blood from a distance greater than that between Earth and the Moon. And yet magnetars are not aggressive. They are not hunting for us. They are simply born that way, the result of specific conditions during the star's collapse. Magnetars also experience starquakes, cracking of their ultra-hard surface, that release enormous bursts of energy. The surface of a neutron star is not like the surface of a rocky planet. It is a crystalline crust of iron and other heavy elements, compressed into a lattice so strong that it makes diamond look like butter. But even that crust can crack under the enormous stresses of the magnet. When it does, the magnetar releases a burst of gamma rays that can outshine the entire galaxy for a fraction of a second. From Earth, we detect these bursts as flashes of high-energy light. They last less than a second, and then they are gone. The magnetar settles back into its quiet state, its crust healing, its magnetic field reconfiguring, waiting perhaps thousands of years before the next crack. A slow, patient cycle of tension and release, like a deep breath held for a millennium and then gently exhaled. Neutron stars are incredibly hot when they are born, but they cool slowly over time. When a neutron star first forms, its surface temperature is about 1 million degrees Celsius. That is not a typo. 1 million degrees. The entire surface of this tiny ball, smaller than a city, glows with the heat of 1 million suns compressed into a single point. But here is the peaceful part. Neutron stars cool remarkably quickly, at least by astronomical standards. Within a few years, the temperature drops to hundreds of thousands. Within 1,000 years, to tens of thousands. Within 1,000,000 years, a neutron star's surface may be only a few thousand degrees, still hotter than the surface of our sun, but no longer blazing with the fire of its birth. Over billions of years, a neutron star cools until it becomes barely detectable, a cold, dark sphere of ultra-dense matter drifting through the galaxy with no light at all. These cold neutron stars are nearly impossible to find because they emit almost no radiation. They are invisible ghosts, the quietest ghosts in the cosmos, passing through the dark without any sign of their existence. Perhaps there are billions of them scattered between the stars. We will never know for certain, and there is something deeply restful about that. The neutron star does not need to be seen. It does not need to announce itself. It simply exists, cool and dark and silent, moving along its orbit with the patience of something that will outlast every human. The first neutron star was discovered in 1967 by a graduate student named Jocelyn Bell. She was using a radio telescope to study quasars, and she noticed a strange, repeating signal in her data. The signal was so regular, so precise, that she and her advisor briefly considered the possibility that it might be a signal from an extraterrestrial civilization. They nicknamed it LGM-1, which stood for Little Green Men. But soon they found another similar signal from a different part of the sky, and then another. It became clear that these were not aliens trying to contact Earth. They were a new kind of astronomical object, a kind that had been predicted decades earlier but never observed. They were pulsars, spinning neutron stars sending out regular beams of radio light. That discovery opened an entirely new window into the. Today we know of more than 3,000 pulsars in the Milky Way galaxy alone. And there are likely hundreds of millions more neutron stars that are not pulsars, either because their beams do not point toward Earth, or because they no longer emit strongly enough to detect. Every one of those neutron stars is a former giant, a star that lived fast and died bright, and then collapsed into something small and strange and lasting. And every one of them spins, slowly or quickly, hot or cold, pulsar or silent. They are the remnants of a more violent time, now settled into a kind of cosmic old age, patient and quiet, and deeply, profoundly still. As you lie here in the dark, imagine all those spinning cores, all those dead stars turned into something new, turning and turning in the great silence between the worlds. Some neutron stars orbit other stars in binary systems. Not all neutron stars are alone. Some were born in pairs, or they captured a companion star after their violent birth. In these binary systems, the neutron star and its companions circle each other, bound together by gravity, moving through space like dance partners in a slow, endless waltz. The orbital periods vary. Some binary neutron stars orbit each other every few hours, their centers separated by only a few 100,000 kilometers. Others take days or weeks to complete a single orbit, drifting far apart, and then coming back together, again and again, for billions of years. In some of these systems, the neutron star pulls material from its companion. The companion star, still burning with fusion, still shining with ordinary starlight, loses some of its outer layers to the intense gravity of the neutron star. That material spirals inward, forming a disk of hot gas around the neutron star before eventually falling onto its surface. As the material falls, it heats up to millions of degrees and emits X-rays. These systems are called X-ray binaries, and they are among the brightest X-ray sources in the sky. But even here, even with gas falling and disks spinning and X-rays shining, there is a kind of peace. The process is steady, predictable. The neutron star takes a little bit of its companion, consumes it, and then waits for more. A slow feeding, a quiet digestion, a relationship between two dead or dying stars that has lasted longer than life has existed on Earth. When two neutron stars orbit each other, they eventually spiral together and collide. This is one of the rarest and most spectacular events in the universe. Two ultra-dense spheres, each the mass of a star but the size of a city, circling each other for millions or billions of years, slowly losing energy through gravitational waves. Gravitational waves are ripples in the fabric of space-time itself, predicted by Einstein more than a century ago, but only directly detected in 2015. As the neutron stars orbit, they radiate gravitational waves, losing energy and spiraling closer and closer. The final moments of such a merger are extraordinary. In the last few seconds, the two neutron stars orbit each other hundreds of times per second, moving at a significant fraction of the speed. Then they touch. Their surfaces merge, their cores combine, and in a flash that lasts less than a second, they release more energy than our sun will produce over its entire 10 billion-year lifetime. This event is called a kilonova. It is 1,000 times brighter than a typical supernova, and it forges the heaviest elements in the universe. Gold, platinum, uranium. All the elements heavier than iron are created in the fiery aftermath of neutron star mergers. Every gold ring ever worn, every platinum wedding band, every uranium atom that powers nuclear reactors, all of it was forged in collisions like this, billions of years ago, in galaxies far from our own. After the merger, one of two things happens. If the combined mass is below a certain threshold, the two neutron stars may form a single, more massive neutron star, spinning rapidly and glowing with. If the combined mass is above that threshold, the merger collapses directly into a black hole, an object even denser and stranger than the neutron stars that came before. Either way, the event is over in less than a second. The gravitational waves ripple outward. The heavy elements scatter into space, and the new object, whatever it is, settles into a quiet existence, perhaps alone, perhaps with a new companion, continuing its journey through the galaxy without any memory of the catastrophic collision that created it. There is something peaceful in that, too. The violence ends. The new object is born. And then silence. Neutron stars are some of the best natural clocks in the universe. Because pulsars spin so regularly, astronomers can use them to measure time with extraordinary precision. In fact, some pulsars are so stable that they rival atomic clocks, the most accurate timekeeping devices humans have. By monitoring the arrival times of pulses from a pulsar over months or years, Scientists can detect tiny changes that reveal the presence of planets orbiting the pulsar, or the influence of gravitational waves passing through our galaxy, or the subtle effects of general relativity and strong gravitational fields. The pulsar does not know it is being used this way. It does not care. It simply spins, emitting its regular beats, a cosmic metronome that happens to be useful to a species of mammals on a small planet in a quiet corner of the galaxy. The first exoplanets ever discovered were found orbiting a pulsar. In 1992, astronomers Alexander Volshan and Dale Frail announced the discovery of 2 planets, and later a third, orbiting a pulsar called PSRB 1257+12. These planets are not like Earth. They are likely dead, irradiated worlds, blasted by the pulsar's intense radiation, with surfaces that may be nothing more than charred rock and frozen gas. It's nonetheless worlds orbiting a dead star. A star that once shone like our sun but now is only a spinning core, smaller than a city, heavier than a mountain, and surrounded by the silent remains of its former solar system. Those pulsar planets orbit very close to their parent star. The innermost planet completes one orbit in just over 25 days, about the same time it takes our sun to rotate once on its axis. But the pulsar's gravity is so intense, and the planets are so close that they experience enormous tidal forces. Their surfaces may bulge and crack with each orbit. Their interiors may be heated by the relentless squeeze of the pulsar's gravity. And yet, they remain. They have remained for billions of years, circling their dead star, carrying on a dance that began when the universe was younger and the star was still alive. There is something almost tender about that, something that invites you to close your eyes and imagine those small, dark worlds turning around their small, bright, pulsing star, a family of cosmic orphans bound together by gravity and time. Neutron stars can have mountains, but those mountains are tiny. On Earth, mountains can be kilometers high. Mount Everest is nearly 9 kilometers above sea level. On a neutron star, gravity is so strong that any mountain taller than a few millimeters would be crushed flat. A few millimeters. That is all the variation the surface of a neutron star can sustain. The rest is smooth to a degree that no natural surface on Earth can match. And yet, those tiny millimeter-scale mountains are enough to create irregularities in the neutron star's spin. As the star rotates, those tiny bumps emit gravitational waves, faint ripples in space-time that carry away energy and cause the star's rotation to slow over time. Detecting those gravitational waves is one of the goals of future observatories. If we can measure the tiny mountains on distant neutron stars, we can learn about their internal structure, their composition, their history. We can learn what happens to matter when it is crushed to densities 1 billion times greater than anything on Earth. But for now, those mountains remain a theory, a prediction, a quiet possibility waiting to be confirmed. Somewhere in the galaxy, a neutron star is turning, and on its surface, a bump no taller than a grain of sand is slowly, gently, emitting ripples in space-time that pass through your body right now as you lie here. You cannot feel them. No human can. But they are there. Evidence of a tiny mountain on a tiny star. A reminder that even the smallest things can have effects that travel across the universe. Neutron stars are so dense that their interiors are unlike anything on Earth. We cannot reproduce neutron star matter in any laboratory. We cannot visit a neutron star. We cannot send a probe. Everything we know about the insides of these objects comes from mathematics, from computer simulations, and from observations of their surfaces, their spins, and their magnetic fields. The leading theory is that a neutron star has a layered structure, like an onion, but made of matter so strange that it defies ordinary description. The outer layer is a thin atmosphere of hydrogen and helium, perhaps only a few centimeters thick, but glowing with heat. Below that is a solid crust of iron and other heavy elements, compressed into a crystalline lattice that is billions of times stronger than steel. This crust is about 1 kilometer thick, and it is where the starquakes happen. Below the crust, things get even stranger. The pressure becomes so intense that atomic nuclei can no longer hold their shape. They are crushed into a sea of neutrons, some of which may form strange structures called nuclear pasta. Nuclear pasta is not a food. It is a theoretical form of matter in which neutrons arrange themselves into long cylinders or flat sheets, like lasagna or spaghetti, but made entirely of subatomic particles. These structures are unimaginably dense and unimaginably strong, and they may fill the outer core of every neutron star. Deeper still, at the very center of the neutron star, the pressure and density become so extreme that even the neutrons themselves may break down into their constituent quarks. Quarks are the fundamental particles that make up protons and neutrons. Under normal conditions, quarks are permanently confined inside larger particles. But inside a neutron star, the density may be high enough to create a quark soup, a liquid of free quarks flowing past each other with no resistance at all. This hypothetical state of matter is called quark matter, and some neutron stars may actually be quark stars, objects even denser and stranger than ordinary neutron stars. We do not know. We may never know. The center of a neutron star is forever hidden from us, locked away behind layers of nuclear pasta and crystalline iron and superfluid neutrons, a mystery at the heart of every dead star. Some neutron stars spin so fast that they are nearly torn apart. The fastest known pulsar, called PSRJ 1748-2446d, spins at more than 716 times. That means its surface is moving at about 24% of the speed of light. At that speed, the centrifugal force at the equator is enormous. If the neutron star spun just a little faster, it would fly apart. The gravity holding it together would no longer be strong enough to overcome the outward pull of its own rotation. This maximum spin rate, called the breakup limit, varies slightly depending on the neutron star's mass and radius, but it is somewhere between 700 and 1,000 rotations per second. No neutron star has ever been observed spinning faster than that limit, which is exactly what we would expect. Nature respects its own boundaries. The fastest pulsars are therefore the ones that are just barely stable, spinning at the edge of disintegration, held together by gravity alone. They are like the fastest possible ice skaters, spinning so quickly that any faster would send them flying apart into a cloud of debris. But they do not fly. They hold together, second after second, year after year for millions of years. They rotate at that incredible speed. Their surface is moving at a quarter of the speed of light, and they remain stable, quiet, almost peaceful, despite the enormous forces trying to tear them apart. Neutron stars slow down over time as they lose energy. Every pulsar spins down gradually. The energy for its beams, its magnetic fields, its gravitational wave emission, all of it comes from its rotation. As the pulsar emits electromagnetic radiation, it loses rotational energy and spins more slowly. This spin down is incredibly gradual. A typical pulsar might take millions of years to slow down by just a fraction of a percent, but over billions of years the effect accumulates. The fastest pulsars are young, recently born in supernovae, still spinning with the energy of their violent birth. Older pulsars spin more slowly. The oldest pulsars, billions of years old, may spin only once every few seconds, or even once. Eventually they spin so slowly that their beams become too weak to detect. They cross the pulsar death line, a theoretical boundary beyond which the mechanisms that produce the beams can no longer operate. The neutron star continues to spin, but it is no longer a pulsar. It becomes a silent, dark sphere, turning slowly in the dark, undetectable by any instrument we currently possess. These dead pulsars may be the most common type of neutron star in the galaxy, but they are also the most invisible. A ghost population of spinning corpses, forever hidden from human eyes. Some neutron stars have been observed glitching, suddenly spinning faster for no apparent reason. A glitch is a sudden increase in the rotation rate of a pulsar, typically by a few parts per million. It happens in an instant, and then the pulsar resumes its gradual spin down, as if nothing had occurred. Astronomers believe that glitches are caused by the interaction between the neutron star's solid crust and its superfluid. The superfluid, which flows without friction, rotates at a different speed than the crust. Occasionally, the excess angular momentum in the superfluid is transferred to the crust in a sudden burst, causing the entire star to spin slightly faster. These glitches are unpredictable and rare, but they have been observed in dozens of pulsars. After a glitch, the pulsar takes months or years to return to its previous spin-down pattern. Sometimes there are aftershocks, smaller glitches that occur in the weeks following a larger one. The whole process is reminiscent of earthquakes, a slow buildup of stress followed by a sudden release. But on a neutron star, the stresses are unimaginable, and the releases are measured not in centimeters of ground motion, but in changes to the star's entire rotation. And then, after the glitch, the neutron star settles back into its quiet rhythm, spinning and pulsing and spinning again, as if nothing had ever. Neutron stars can tell us about the history of the galaxy. Because pulsars are so regular, and because they do not change much over human timescales, they can be used as cosmic probes. By measuring the arrival times of pulses from pulsars in different parts of the sky, astronomers can map the distribution of gas and dust in the Milky Way. They can measure the strength of the galaxy's magnetic field. They can detect the presence of gravitational waves passing through our cosmic neighborhood. They can even test theories of gravity in ways that are impossible on Earth. Every pulsar is a tiny laboratory, a natural experiment set up by the universe itself, available to any astronomer who knows how to listen. The most precise pulsar timing arrays are like listening for the faint hum of the universe. Astronomers monitor dozens of pulsars simultaneously, measuring their pulse arrival times with nanosecond. They look for correlations in the timing residuals, tiny deviations from perfect regularity that might be caused by gravitational waves passing through our galaxy. These gravitational waves could come from supermassive black hole mergers, from the early universe, or from the inspiral and merger of neutron stars and black holes. In 2023, several pulsar timing arrays announced the detection of a background hum of gravitational waves, a faint murmur that fills the universe, and may be the combined signal of millions of merging supermassive black holes over cosmic history. You cannot hear that hum. No human ear could. But it is there, a low-frequency vibration in the fabric of space-time, passing through you even now. Neutron stars are also used to test Einstein's theory of general relativity in extreme conditions. General relativity predicts that clocks run slower in strong gravitational fields. On Earth, this effect is tiny but measurable. Near a neutron star, the effect is enormous. A clock placed on the surface of a neutron star would run significantly slower than a clock far away. Similarly, the path of light near a neutron star is bent dramatically by gravity. A beam of light passing close to a neutron star would be deflected by an angle much larger than the deflection caused by our sun. By observing pulsars and binary systems, astronomers have confirmed these predictions with exquisite precision. Einstein's theory holds up even in the most extreme gravitational environments we can study, a testament to its deep and enduring truth. In some binary systems, the timing of the pulsar's pulses can be used to measure the mass of both stars to extraordinary precision. The most famous such system is the Hulse-Taylor binary, a pair of neutron stars that orbit each other every 7 hours and 45 minutes. By monitoring the arrival times of pulses from one of the neutron stars for decades, astronomers measured a tiny decay in the orbital period, exactly the amount predicted by general relativity for a system losing energy through gravitational. Russell Hulse and Joseph Taylor won the Nobel Prize in Physics in 1993 for this discovery, which provided the first indirect evidence for the existence of gravitational waves. The pulsars themselves did not know they were making history. They simply orbited each other, as they had done for millions of years, their dance a silent testament to the strange and beautiful laws that govern our universe. Some neutron stars are born with extremely weak magnetic fields, and these are among the quietest objects in the galaxy. Not every neutron star is a pulsar or a magnetar. Some have magnetic fields only a few million times stronger than Earth's, which sounds enormous until you compare it to the trillions of times stronger fields of ordinary pulsars. These weakly magnetized neutron stars are nearly impossible to detect. They do not pulse. They do not flare. They do not heat their surroundings. They simply exist, cold and dark and silent, drifting through the galaxy like cosmic. There may be hundreds of millions of them, far outnumbering the pulsars we can see. We know these weakly magnetized neutron stars exist because of a few chance encounters. In some cases, one of these dark neutron stars has passed between Earth and a more distant source of radio waves, and its gravity has bent and focused those waves in a way that astronomers could detect. This is called gravitational lensing, and it is one of the few ways to find objects that emit no light of their own. Each such detection confirms that there are more neutron stars in the galaxy than we can see, a hidden population of silent spinning remnants, each one a former star that lived and died, and now drifts through the dark without any sign of its existence. As you close your eyes, imagine those hidden spheres, turning slowly, invisibly, like ghosts in a graveyard of giants. The closest known neutron star to Earth is about 400 light-years away. That sounds impossibly far. And in human terms, 400 light-years is more than 2,000 trillion miles. But on a galactic scale, that is very close. The Milky Way is more than 100,000 light-years across. A neutron star 400 light-years away is in our cosmic neighborhood, practically next door. This nearby neutron star is called Calvera, and it was discovered in 2007 by a team of astronomers using the Rossi X-ray Timing Explorer satellite. Calvera is an isolated neutron star, meaning it has no companion, no disk, no signs of recent accretion. It is just there, alone in the dark, emitting faint X-rays that we can barely detect. There may be neutron stars even closer to us, hidden by their own darkness. The galaxy is vast, and we have only surveyed a tiny fraction of it. There could be a neutron star within 100 light-years of Earth, or within 50, or within 10. We would not necessarily know. An old, cold, non-pulsing neutron star would be nearly invisible to our It could drift through the outer reaches of our solar system, passing beyond the orbit of Pluto, and we might never detect it. The odds of such a close encounter are extremely low, but they are not zero, and there is something both unsettling and peaceful about that thought. A dead star, smaller than a city, heavier than the sun, could be passing through our cosmic backyard right now, and we would have no way of knowing. But even if it were, it would not harm us. It would simply drift, silent and patient, carrying its impossible density through the quiet dark. Neutron stars are also some of the best natural accelerators in the universe. The electric and magnetic fields around a pulsar can accelerate particles to energies far beyond anything humans have achieved in our largest colliders. These accelerated particles, mostly electrons and positrons, stream away from the pulsar at nearly the speed of light, creating glowing nebulae called pulsar. The most famous example is the Crab Nebula, the remnant of a supernova observed by Chinese astronomers in the year 1054. At the center of the Crab Nebula is a pulsar that spins about 30 times per second. That pulsar drives the entire nebula, injecting energy in the form of particles and magnetic fields that make the gas glow in almost every wavelength of light. The Crab pulsar is also one of the most studied objects in the sky. It was one of the first pulsars discovered. It has been monitored continuously for decades. It occasionally produces giant pulses, bursts of radio emission that are thousands of times brighter than its ordinary pulses. It also produces optical pulses, X-ray pulses, and gamma-ray pulses, making it one of the most versatile cosmic lighthouses in existence. And yet, despite all that activity, despite the radiation and the particles and the glowing nebula, the Crab pulsar itself is only about 20 kilometers across. All that energy, all that light, all that history comes from a sphere no larger. For nearly 1,000 years, it has spun and pulsed and driven its nebula, and it will continue to do so for millions of years to come, long after every human alive today is gone, long after our species may have vanished from the universe entirely. Some neutron stars produce jets, narrow beams of matter and energy shooting out from their magnetic poles. These jets are similar to the jets produced by black holes, but on a smaller scale. They are formed when material from a companion star falls onto the neutron star, heating up and being channeled along the magnetic field lines toward the poles. There, it is ejected into space at speeds close to the speed of light, creating twin beams of plasma that can extend for light years. These jets are not steady. They flicker and change, responding to variations in the flow of material from the companion star. But over long timescales, they are remarkably persistent, drilling holes in the surrounding gas and shaping the environment around The study of neutron star jets is a young field, and many questions remain unanswered. How are the jets launched? How much power do they carry? What determines their speed and collimation? Each new observation offers a piece of the puzzle, but the full picture remains hidden. What we do know is that these jets are among the most efficient engines in the universe, converting the gravitational energy of infalling gas into kinetic energy with remarkable efficiency. And when the flow of material stops, when the companion star finally gives up its last gas, the jets fade and die. The neutron star returns to its quiescent state, spinning quietly, its magnetic fields no longer fed by fresh matter, its jets nothing more than a memory. The cycle may begin again if a new companion is captured, or it may end forever, leaving the neutron star alone in the dark for the rest of its long, long life. Neutron stars can also have rings of debris around them, similar to the rings of Saturn, but made of much denser. These rings are formed when a companion star is torn apart by the neutron star's gravity, or when material from the companion's stellar wind is captured and forms an accretion disk. The inner part of the disk spirals inward and eventually falls onto the neutron star. The outer part may remain stable for millions of years, a thin, hot ring of gas and dust circling the dead star at enormous speeds. These rings are visible in X-rays and ultraviolet light, glowing with the heat of friction and compression. They are beautiful in their own violent way, and they tell us about the history of the binary system and the fate of the companion star. Over time, the rings decay. Material falls inward. The disk thins and fades. Eventually, nothing remains except the neutron star itself, alone again, its companion fully consumed. This is the inevitable fate of most binary neutron star systems. The more massive star dies first, becomes a neutron star, and then slowly devours its. The companion may become a neutron star too, leading to a double neutron star system like the Hulse-Taylor binary. Or the companion may be completely consumed, leaving only a single neutron star spinning in the dark. The process takes millions or billions of years, but it always ends the same way. The neutron star outlives everything around it. It is a survivor, a remnant, a core of matter that has persisted through the death of its parent star, the death of its companion, the death of any planets that may once have orbited it. And still it spins, still it endures, still it drifts through the galaxy, waiting for whatever comes next. Some neutron stars travel through the galaxy at incredible speeds, kicked by the supernova that created them. When a star collapses, the explosion is not always perfectly symmetrical. If more material is ejected in one direction than another, the neutron star at the center gets a kick in the opposite direction, like a rocket engine. These kicks can propel neutron stars to speeds of hundreds or even thousands of kilometers per second. A neutron star moving at 1,000 kilometers per second will cross the entire Milky Way in less than 100 million years. It may escape the galaxy entirely, becoming a rogue neutron star drifting through intergalactic space. We have observed several hypervelocity neutron stars, moving so fast that they will eventually leave the galaxy. One of them, called RxJ0822-4300, is moving at more than 1,500 kilometers per second, fast enough to travel from Earth to the Moon in less than 5 minutes. It was kicked by the supernova that created it about 4,500 years ago, and it is already more than 100 light-years from its birthplace. In a few million years, it will exit the Milky Way and begin a long, lonely journey through the void between. There, in the darkness, it will spin for billions of years, perhaps trillions of years, with nothing around it but the faint glow of distant galaxies and the cold whisper of the cosmic microwave background. These runaway neutron stars are among the loneliest objects in the universe. They have no companions. They have no planets, at least none that could survive the supernova. They have no nebulae, no disks, no rings, no jets. They are just bare spheres of ultra-dense matter, hurtling through space at speeds that human spacecraft could never match. And yet they are not unhappy. They do not feel loneliness. They do not yearn for company. They simply exist, moving along their trajectories, obeying the laws of physics, spinning and cooling and becoming ever fainter. There is something peaceful in that, too. A neutron star does not need a purpose. It does not need to be seen or loved or remembered. It simply is, a fact of the universe, as real as gravity and as patient as time. Some neutron stars are born in dense star clusters, where they may capture new companions after their original ones are. Globular clusters are ancient balls of hundreds of thousands of stars, packed together so tightly that stellar encounters are common. If a neutron star is born in a globular cluster, it may interact with other stars over the cluster's 11 billion-year history. It may capture a new companion, stripping gas from a passing star and becoming a bright X-ray source for a few million years. It may merge with another neutron star, creating a black hole and releasing gravitational waves. It may be ejected entirely, kicked out of the cluster by a close encounter with another star. The possibilities are endless. In globular clusters, neutron stars can also form exotic binary systems, such as black widow pulsars or redback pulsars. In these systems, the pulsar is slowly evaporating its companion, using its intense radiation to boil away the companion's outer layers. The companion, usually a low-mass star, is being destroyed from the outside in, losing mass at an enormous... Eventually, the companion may be completely consumed, leaving the pulsar alone again. But before that happens, the system may go through phases of intense activity, with the pulsar's radiation heating the companion to tens of thousands of degrees and causing it to glow brightly. These systems are among the most dynamic in the galaxy, changing on timescales of years or even months. And yet, even here, even in the midst of evaporation and destruction, there is a kind of order. The pulsar spins, the companion orbits, the radiation does its work, and the system evolves, slowly, inexorably, toward its inevitable end. Neutron stars can also be used to search for dark matter. Dark matter is the mysterious substance that makes up most of the mass of the galaxy, but does not emit, absorb, or reflect any light. We do not know what dark matter is, but we know it is there because of its gravitational effects. If dark matter consists of particles, some of those particles might occasionally pass through a neutron star and be... Over time, captured dark matter particles would accumulate in the neutron star's core, where they could annihilate with each other, producing heat and potentially changing the neutron star's observable properties. By studying the temperature and spin of old cold neutron stars, astronomers can place limits on the properties of dark matter particles. So far, no neutron star has shown unambiguous evidence of dark matter heating. The limits are getting stronger, but the signal remains elusive. Dark matter may be harder to detect than we thought, or it may not consist of particles that interact strongly enough to be captured by neutron stars. Or perhaps the dark matter is there, but the heating is too subtle for our current instruments to detect. The search continues, and in the meantime the neutron stars spin on, unperturbed by the dark matter that may or may not be passing. They are patient laboratories, waiting for us to ask better questions, to build better instruments, to listen more carefully. They will wait as long as we need them to. They have time. The magnetic fields of neutron stars can also produce light in unexpected ways. One of the most beautiful phenomena associated with pulsars is called optical pulsation. In a handful of pulsars, including the Crab and the Vela pulsar, is visible in optical light, not just in radio or X-rays. These optical pulsars appear to blink on and off as they spin, hundreds of times per second. The human eye cannot see these blinks. They are far too fast. But if you could slow down time, if you could watch a pulsar spin in slow motion, you would see it flash and fade, a cosmic strobe light in the dark. Some pulsars also emit gamma rays, the most energetic form of light. The Fermi Gamma Ray Space Telescope has discovered hundreds of gamma ray pulsars, many of which are invisible in radio waves. These are called radio-quiet pulsars, and they may represent a majority of the pulsar population. Their beams are oriented in such a way that they sweep past Earth in gamma rays, but not in radio frequencies. Finding them requires different techniques, but once found, they reveal themselves as some of the most extreme objects in the galaxy. A gamma ray pulsar is a natural particle accelerator, converting the energy of its rotation into beams of light that can be detected across the galaxy. And still, despite all that energy, the pulsar itself is only 20 kilometers across. Small, dense, and powerful beyond comprehension. Neutron stars also help us understand the behavior of matter under extreme pressure. The interiors of neutron stars are the closest thing we have to a laboratory for studying quantum chromodynamics, the theory of the strong nuclear force, under conditions that cannot be created on Earth. The density inside a neutron star is higher than the density inside atomic nuclei. At those densities, matter behaves in ways that are still not... Do quarks become deconfined, forming a quark liquid? Do strange quarks appear, creating strange matter that might be even more stable than ordinary nuclear matter? Do the neutrons form superfluids that flow without friction? These are not idle questions. They go to the heart of how matter behaves at its most fundamental level. The answers may come from observing neutron star mergers. When two neutron stars collide, their combined density and temperature briefly exceed anything that can be achieved in a human laboratory. The electromagnetic signal from the merger, the kilonova, carries information about the equation of state of neutron star matter, the relationship between pressure and density. By studying kilonovae with telescopes that observe in optical, infrared, and X-ray light, astronomers can infer the properties of matter under extreme. The first kilonova that was observed in both gravitational waves and electromagnetic radiation, called GW 170,817, has already provided important constraints on the neutron star equation of state. Future observations, with more sensitive instruments, will narrow those constraints further, perhaps eventually telling us exactly what lies at the heart of every neutron star in the universe. Neutron stars also have a maximum mass. If a neutron star becomes too heavy, its own gravity overwhelms the forces that hold it up, and it collapses into a black hole. This maximum mass is not precisely known, but it is somewhere between 2 and 3 times the mass of our Sun. The most massive neutron stars ever observed have masses of about 2.1 or 2.2 solar masses. Heavier than that, and they would likely collapse. The existence of this maximum mass is a consequence of general relativity and the properties of nuclear matter, and it means that neutron stars are not infinitely stable. They have a limit. Beyond that limit, they become something. When a neutron star collapses into a black hole, the transition is swift and silent. The neutron star does not explode. It does not flash. It simply shrinks. One moment, it is a sphere of neutron matter, 20 kilometers across. The next moment, it is a singularity, a point of infinite density wrapped in an event horizon. The entire process takes less than a second. And after it is over, nothing remains of the neutron star except its gravitational field, and possibly some material that was in the process of falling onto it. The black hole that forms is small, only a few kilometers across, but it is a black hole nonetheless, an object from which nothing, not even light, can escape. And yet even that is not an ending. The black hole will persist for billions or trillions of years, slowly evaporating via Hawking radiation, eventually disappearing in a final flash of light long after the rest of the universe has grown cold and dark. Some neutron stars may be partly made. Strange matter is a theoretical form of matter that contains strange quarks in addition to up and down quarks. Strange quarks are heavier than up and down quarks, but under extreme density and pressure, it may be energetically favorable to convert some of the down quarks into strange quarks. If that happens, the resulting strange matter might be even denser and more stable than ordinary neutron matter. A strange star would be similar to a neutron star, but with a different internal structure and possibly a different maximum mass. There is also a speculative idea called the strange matter hypothesis, which suggests that strange matter might be the absolute most stable form of matter in the universe. If that is true, then any neutron star that touches a piece of strange matter would be converted into strange matter in a chain reaction that spreads through the entire star. The resulting strange star would be stable, but the conversion process would release enormous amounts of energy, possibly destroying the star. Never been observed, and most astronomers consider the strange matter hypothesis to be unlikely. But it is not impossible, and until we understand the interior of neutron stars better, we cannot rule it out entirely. The universe is full of surprises, and neutron stars are among the most surprising objects in it. Neutron stars also help us measure the expansion of the universe. Some pulsars are so regular that they can be used as standard candles, objects whose intrinsic brightness is known. By measuring how bright they appear from Earth, astronomers can calculate their distance, and by measuring the distances to pulsars in other galaxies, astronomers can calibrate the cosmic distance ladder, the series of methods used to measure distances to faraway galaxies. This calibration is essential for measuring the Hubble constant, the rate at which the universe is expanding. Different methods of measuring the Hubble constant give slightly different answers, and that discrepancy, called the Hubble tension, is one of the biggest puzzles in cosmology today. Pulsar timing can also be used to measure the mass of the Milky Way's supermassive black hole. By observing pulsars that orbit close to the galactic center, astronomers can trace the gravitational field of the black hole and measure its mass with precision. The supermassive black hole at the center of the Milky Way, called Sagittarius A, has a mass of about 4 million suns. Pulsar timing has confirmed this mass and will eventually measure it with even greater precision. In the future, a pulsar orbiting very close to the supermassive black hole could be used to test general relativity and the strongest gravitational field in the galaxy. providing a unique window into the nature of space and time near an event horizon. Some pulsars have been observed to have planets, and these planets are among the strangest worlds. The planets orbiting the pulsar PSRB 1257+12 have masses comparable to Earth's moon and to Mars. They are probably composed of carbon and oxygen, the remnants of a white dwarf that was destroyed by the pulsar. Their surfaces are likely covered in graphite and diamond, a layer of crystalline carbon that may be kilometers thick in places. Imagine a world made of diamond, orbiting a dead star, with a sky that pulses with radiation hundreds of times per second. It is a scene unlike anything in our solar system, a world from the strangest corners of the imagination made real by the laws of physics. Other pulsar planets may be even stranger. Some could be Chthonian planets, the stripped cores of gas giants that lost their atmospheres to the intense radiation of the pulsar. Others could be captured planets, wandering worlds that strayed too close to the pulsar and were trapped by its gravity. Still others could be second-generation planets, formed from debris left over after the supernova that created. Each possibility is more exotic than the last, and each tells us something different about the history of the pulsar and its environment. The universe does not lack for wonders. It simply hides them in plain sight, waiting for curious minds to look closely. Neutron stars can also be used to test the equivalence principle, one of the foundations of general relativity. The equivalence principle states that gravitational mass and inertial mass are the same, meaning that all objects fall at the same rate in a gravitational field, regardless of their composition. By observing a pulsar in a binary system with a white dwarf, and comparing the arrival times of pulses from the pulsar to the orbital motion of the system, astronomers can test whether the neutron star and the white dwarf fall at the same rate. So far, all tests have been consistent with the equivalence principle to within a few parts per million. Einstein passes another test, and the universe remains consistent. Stars are part of triple systems, where three stars orbit a common center of mass. These systems are rare but extremely valuable for testing theories of gravity because they offer more constraints than binary systems. The most famous triple system containing a pulsar is PSRJ 0337 plus 1715, which consists of a pulsar, a white dwarf, and another white dwarf in a hierarchical orbit. By monitoring the arrival times of pulses from the pulsar for many years, astronomers have confirmed that the system behaves exactly as general relativity predicts, with no evidence for deviations that would suggest alternative theories of gravity. The pulsar is a silent witness, its regular beats revealing the intricate dance of three stars bound together by gravity across billions of years. Neutron stars also produce particles called neutrinos, which are among the most elusive particles in the universe. When a neutron star is born in a supernova, most of the energy of the explosion is carried away by neutrinos, not by light. In fact, the neutrinos from a supernova are so numerous that they can affect the evolution of the explosion itself. The neutrino burst from a supernova is also one of the few signals that can escape the dense core of the star almost unimpeded, reaching Earth before the light from the explosion. Detecting these neutrinos would give us a direct window into the heart of a collapsing star, revealing details about the birth of neutron stars that cannot be obtained in any other way. The only supernova from which we have detected neutrinos was SN 1987A, which occurred in the Large Magellanic Cloud, a satellite galaxy of the Milky Way. On February 2003, 1987, 3 neutrino detectors around the world recorded a burst of neutrinos coming from the direction of the supernova. Those neutrinos arrived hours before the light from the explosion, and they provided the first direct evidence that neutron stars are born. The neutrino burst lasted only a few seconds, but it changed our understanding of stellar death forever. Today, new neutrino detectors are online, and they are waiting for the next nearby supernova. It could happen tonight, or in 1,000 years. Whenever it happens, the neutrinos will arrive first, carrying the news of a new neutron star's birth. Neutron stars are also sources of cosmic rays, high-energy particles that travel through the galaxy at nearly the speed of light. The particles accelerated by pulsars, especially young, energetic pulsars like the one in the Crab Nebula, can reach energies that are beyond anything achievable on Earth. These cosmic rays travel through the galaxy, some of them eventually reaching Earth's atmosphere, where they create showers of secondary particles that can be detected by ground-based observatories. Every second, cosmic rays from pulsars and other sources pass through your body, leaving no trace except the faintest possibility of a collision with an atom. You have been touched by dead stars with the body, the air in your lungs, the ground beneath your home. All of it has been shaped by the same cosmic processes that create neutron stars. The study of neutron stars is a young science, barely more than half a century old. In that time, we have gone from not knowing they existed to discovering thousands of them, mapping their properties, and using them as tools to probe the fundamental laws of physics. And yet, for all we have learned, there is still so much we do not know. What is the equation of state of neutron star matter? What is the maximum mass of a neutron star? What happens inside a neutron star when it glitches? How many neutron stars are there in the galaxy? What is the true nature of dark matter? Neutron stars are helping us answer these questions, but they are also raising new ones. That is the nature of science. Each answer leads to deeper questions, and each deeper question leads to a fuller understanding of the universe we inhabit. Somewhere in the galaxy, a neutron star is spinning. Perhaps it is a young pulsar, blazing with energy, its beams sweeping through space like the light of a forgotten lighthouse. Perhaps it is an old, cold neutron star, dark and silent, drifting through the void with no one to see it and no one to care. Perhaps it is part of a binary system, orbiting a companion that feeds it gas and makes it shine in X-rays. Perhaps it is alone, ejected by the supernova that created it, hurtling toward the edge of the galaxy and beyond. Whatever it is, wherever it is real. It exists. It spins, and it will continue to spin, long after you have fallen asleep, long after you have woken tomorrow, long after every human alive today is gone. The neutron star does not know you exist. It does not know about Earth or life or the small concerns of your day. It does not care about your worries, your regrets, your hopes for tomorrow. It simply turns, bound by gravity and quantum mechanics, a sphere of matter so dense that it bends the fabric of space-time around it. And there is a profound peace in that. The universe is vast, the galaxy is ancient, the neutron star is indifferent. And you, for a few hours, are allowed to let go of everything that is not this moment, this breath, this quiet drift towards sleep. The Milky Way contains perhaps 1 billion neutron stars. That is 1 billion dead stars spinning in the darkness of our galaxy alone. Most of them are invisible to us, too old, too cold, too faint to be detected, but they are there. Every one of them is a former sun, a star that shone for millions or tens of millions of years before collapsing into this smaller, denser, stranger form. Every one of them carries the memory of its birth, the supernova that created it, the elements it forged and scattered into space. Every one of them is a chapter in the long story of our galaxy, a story that began more than 13 billion years ago and will continue for billions of years after. And you, tonight, are part of that story too. The atoms in your body were forged in stars, some of which may have become neutron stars. The iron in your blood was created in the heart of a massive star that died in a supernova, scattering its iron across space. Some of that iron eventually found its way to Earth, into the oceans, into the food you eat, into your body. You are made of stardust. You are made of the same elements that neutron stars are made of, only arranged differently, more loosely, more temporarily. You are a temporary gathering of stardust, a brief pattern of atoms that will eventually return to the universe. And in that sense, you are not separate from the neutron stars. You are part of the same cosmic cycle, the same grand recycling of matter that has been going on since the first stars ignited. When you fall asleep tonight, when you drift into dreams, the neutron stars will still be spinning. They will not notice your absence. They will not know that you have let go. They will simply continue, as they have continued for millions or billions of years, turning and pulsing and drifting through the dark. There's a kind of companionship in that, a kind of silent solidarity. You are not alone in your turning. The Earth turns. The solar system turns. The galaxy turns. And at the heart of that turning, neutron stars spin, small and dense and quiet, bearing witness to the passage of cosmic time. Perhaps, in your dreams tonight, you will visit a neutron star. You will stand at a safe distance, watching it spin, watching its beams sweep past you like the light of a distant lighthouse. You will feel nothing, hear nothing, Only see the silent turning of that impossible sphere, and you will know that you have seen something real, something that exists out there in the galaxy, something that will outlast every human who ever lives. That knowledge it is the peace of understanding your place in the universe, not as the center of everything, but as a small part of something vast and beautiful and enduring. The neutron star does not ask anything of you. It does not demand your attention, your worship, your understanding. It simply exists, and you are free to ignore it or to contemplate it as you drift toward sleep. Tonight, you have chosen to contemplate it. You have let its strange properties fill your mind, not with anxiety or excitement, but with a calm, quiet wonder. And that wonder has carried you here, to the edge of sleep, where the mind finally lets go and the body rests. That is the gift of neutron stars. They remind us that the universe is full of things we do not understand, and that is okay. We do not need to understand everything. We only need to rest. Some cultures have seen dead stars as ancestors watching over the living. Others have seen them as distant campfires, the lights of other worlds. We know now that neutron stars are neither. They are natural objects, governed by the same laws of physics that govern everything else. But there is still a kind of poetry in them. They are the graves of giants. They are the coldest, densest, quietest places in the universe. They are the clocks by which the galaxy keeps time. And they are there, above you, around you, beneath the surface of the visible sky, turning in the dark. As this journey comes to a close, as your breathing slows and your eyelids grow heavy, remember that you are not leaving the neutron stars behind. They will be there when you wake. They will be there tomorrow night and the night after, and for all the nights of your life. They are constant in a way that almost nothing on earth is constant. They are patient. They are enduring, and they are quiet as the space between your thoughts. So let go now. Let go of the day, let go of tomorrow, let go of every worry, every plan, every unfinished task. They will still be there when you wake. For now there is only this, the dark. The soft turning of the earth beneath you, and somewhere, far away, a neutron star spins, small and dense and silent, keeping time for no one but itself. If you are still awake, you can let the sound of my voice carry you the rest of the way. You do not need to listen to the words anymore. You only need to rest. Let the rise and fall of the sentences become a gentle rhythm, like breathing, like waves on a distant shore, like the slow rotation of a dead star in the dark. Sleep well, dream softly, and know that somewhere in the galaxy, a neutron star is spinning, and you, for this brief moment, are part of the same universe.